Our next speaker is Benika Hall. She's Senior Data Scientist and Solutions Architect at NVIDIA, formerly at Wells Fargo. She went to UNC Charlotte for a PhD in bioinformatics. And I told her, I'm like, you're kind of all over. Like, you got vertical agnosticity going here. And she loves sports analytics. So please welcome Benika Hall.
Thank you, everyone. Can you all hear me? Good, good. Yes, love sports analytics. I'm very well-rounded, so all things sports, any sport, we can catch up about it. But so today I wanted to share with you some best practices for model deployment on GPUs. I know you've heard a lot of talks about model development, model training, so I want to talk to you about what comes after. So we'll start with some challenges in inferencing. We'll discuss what is an inference server, and then go into the best practices when deploying scalable multiple models. And if we have time, I'll show just a few slides on achieving better performance, given the best practices that we employ. So I like to start with some of the challenges we have in model deployment. As data scientists, the first one is something I think we all can relate to, and that is the usability. I can't count on the number of times that I've seen teams use multiple frameworks, PyTorch, TensorFlow, MXNet, or XGBoost, and LightGBM. So a lot of times we have to have a solution that allows us to handle these multiple frameworks. In addition, not all use cases are the same. So some use cases require different different queries. So for instance, if you have something like a call center transcription, you may want real-time inference. So you'll need to get those requests back as soon as possible or instantly. In other scenarios, you can do batch inference. So, this is a challenge, where we have to find a solution that allows us to handle different types of queries. Next is the cost of deployment. So the cost of deployment, it grows pretty fast. A lot of times you have scenarios where there are separate solutions for GPU or CPU. In addition, you may have something that's fit for the cloud. So you'll have these hybrid cloud environments. So these types of costs can grow pretty fast. And another challenge that we've seen is, a lot of data scientists work with ecosystem tools. So we need something that can integrate with these ecosystem tools as well as cluster orchestration tools. So if you've heard of Kubernetes. So what I'm going to talk to you about will kind of help us address these challenges today. So, how do we address these challenges? And if you see the image on the slides, I'm going to talk about Triton Inference Server. Now, what is Triton Inference Server? I don't know how many of you have ever heard of, HTTP requests and things like that. Show of hands. Okay, good. So that's what I want you to kind of have in mind as I go through this. So Triton Inference Server, as you see on the left here, we have a Python client. Now this Python client allows us to submit inference requests via a HTTP or a gRPC protocol. Those requests are then, conducted in different types of batch modes. So it could be in real time, batch, or streaming. Now, based on the model type, the inference server will schedule those queries one out of two ways. It will do it in a serialized fashion or execute those requests in parallel. And we'll kind of get into how this is done a little later and what the benefits are. And so, as I mentioned, one of the challenges is being able to handle multiple frameworks. So with Triton Inference Server, I'm allowed to deploy multiple models, whether it's PyTorch, TensorFlow, XGBoost, or LightGBM, just within one inference server. And once again, this can all be done on either GPU or CPU. So there are no limitations. You don't have to deploy this on GPU directly. You can use this within a CPU environment. And so here, I kind of want to reiterate, why this is important. We want to standardize our inference platform. A lot of times, in my former roles, I've seen, a lot of different solutions or multiple platforms that just weren't scalable. So we want to standardize our platform. We need something that can handle multiple frameworks. We need something that can give us the opportunity to deploy and run inference on GPU or CPU, also on the cloud, whether it's AWS, GCP, or Microsoft Azure. The next thing is, we need to be able to handle different types of queries. So whether that's in real time or streaming or in batch inference. And the last thing is we want to make sure that we can maximize our hardware utilization. That way we can lower our total cost of operation when using GPUs. Okay, so now let's dive into some of the best practices. And today we're gonna cover 5, and for the sake of time, we'll try to be concise. And I want you to have some key takeaways with this talk today. So the first one is multiple instance groups, and multiple instance groups it's a configuration that allows us to specify how many parallel executions that should be allowed for that particular model. The next one is dynamic batching. So dynamic batching allows us to submit these inference requests, and then they're grouped and combined on the server, but it creates these batches dynamically, so allowing us to stay within our GPU limitations. Oh, sorry, wrong thing. Ensemble models. So ensemble models is a feature that lets us group together different steps in a pipeline. So an ensemble model represents a pipeline or one or two models and the connection of input and outputs between those two models. And the last two is business logic scripting. So business logic scripting allows us to add some custom flow logic. There are some cases where we may have loops and conditionals before we need to run inference on these models. So with business logic scripting, we can achieve that with the model execution. And the last thing is the model analyzer. As data scientists, we like to evaluate things. So the model analyzer gives us the optimal configuration to increase throughput and reduce our latency for execution. Okay, so let's dive right into the first best practice, and that is dynamic batching. So within Triton Inference Server, we have a dynamic batching scheduler. And so what that does is it groups the requests that we submit to the inference server into larger batches, and that allows us to increase the GPU utilization. So what happens is when we submit the independent requests, the client groups them together into a single batch, thus increasing the GPU utilization. And one must specify, we must give it the preferred batch sizes before it begins to execute and generate these dynamic batches. And so we'll see some results on how that increases our GPU utilization. And that's here. So this is actually on, we'll have 2 of these. This is actually on one of our T4 architectures. Now, in this image here, in this chart, we have on the x-axis, we have the concurrent client requests, and on the y-axis, we're seeing the inferences per second. So after we define our batch size and we specify any latency threshold or restrictions we have, we can then enable dynamic batching in order to increase our throughput. So if you look here, the blue line shows us just a static request with dynamic batching, and we can achieve 2.5 times faster inferences per second with a 50 millisecond end-to-end server latency threshold. This was actually done on a T4 architecture. Okay, and so this is a similar image, same scenario, but this is on a newer architecture from the T4, the V100s. So same thing here, the blue line shows a static batch size of 1 with dynamic batching enabled, and then the red line shows us the static of a batch size 8 with no dynamic batching. So if you see, we can achieve more inferences per second, by enabling dynamic batching. Okay, so the next best practice is concurrent model execution. So we talked about being able to execute multiple models or multiple instances of the same model. And this is how we can achieve that. So concurrent model execution allows us to execute multiple models either in 2 ways. The first, as you can see in the image on the left, is a serialized execution. And how this works is that if multiple requests arrive at the inference server at the same time, the scheduler will then execute those requests one at a time. On the other hand, if we have multiple requests that arrive at the inference server, the first 3, as you can see in the image here, the first 3 Model 1 inference requests are immediately executed, while the 4th Model 1 inference request has to wait until one of the first 3 have been completed. So by doing this, we can reduce the inference time per model. Okay, so another best practice is model ensembling. So this is a great feature if you have multiple steps that you have to encapsulate in your process. For instance, if you're doing data pre-processing, and then you run inference, and then you have a post-processing step. Model ensembling allows us to control the flow of data between these models. And what happens is it chains the inputs and the outputs together for each model into a single model. So the inference server sees all 3 models combined as a single model, giving us a single output. And each model in the pipeline can actually run on a separate framework as well as a different hardware. For instance, if you're running your pre-processing and you need to run it on CPU, you may not need GPU for that. So you can run a pre-processing pipeline in a separate framework from your actual model. Let's say you have a PyTorch model and you need the PyTorch model to execute on GPU. That's not a big deal for using Triton Inference Server. It can handle it. And by using the model ensembling feature, this helps us avoid the overhead of transferring intermediate results between with GPU memory and minimize the number of requests that we send to the inference server. Okay. And so the last best practice is called the model analyzer. So as I mentioned before, we like to evaluate the metrics and we need to understand, what our optimal model configuration is before we deploy the model into production. So this is a tool that automatically identifies those model configurations given the GPU memory requirements that we have. So first we have to specify the constraints. Let's say we must execute these models within a 50 millisecond threshold. These are the restraints that we have to pass to the Triton Inference Server. And if there are any latency or throughput requirements, we can specify this with the model analyzer. And what happens is the model analyzer will sweep through different combinations based on the batch sizes that we specify, the number of model instances for each model, as well as the concurrency of the client requests. And what happens is it finds the best configuration for optimal performance under the given constraints. And it gives us this nice report and charts as you see on the right here. So the chart shows us the throughput versus the latency for the top 3 model configurations. And that gives you, it saves a lot of time in guessing, how many model instances we should run or the memory that we have on the GPU. Okay, so just wanted to recap just the benefits of the model analyzer. So the model analyzer lets us measure the GPU memory footprint for the model for different batch sizes and the concurrency requests. These results help us identify the optimal model configuration, which allow us to maximize the performance and increase our GPU throughput. The second thing, it helps us optimize the hardware usage, so we can determine the maximum number of models or model instances that can be loaded per GPU, thus reducing the hardware needed. If you think about, I've seen some situations where we'll have data scientists request all 8 GPUs, but they only need 1 GPU. Their models won't fit on all 8. It's just 1 is required. 1 is enough. So with that, we can reduce the number of hardware that's needed. The third thing is maximizing the hardware throughput, the model throughput. So this ensures that the models placed on each GPU do not exceed the sum of the memory and GPU utilization. So this helps us increase or maximize the throughput for our hardware. And the last two, increase reliability. By understanding our hardware limitations beforehand, we can eliminate the out-of-memory errors by knowing that the models we load on that GPU will not exceed the GPU memory available. And lastly, the better hardware sizing. We can determine the exact amount of hardware needed to run our models using the given memory requirements. Okay, so here, just gonna go through just a few performance scenarios. This slide here is showing us a concurrent model execution of a ResNet 50 model. So this was done on the TensorRT backend. And the scenario is that we have 12 instances of this particular model. And each instance takes 1.33 gigabytes to load on a GPU. Now we are submitting 14 concurrent requests. So out of those 14 concurrent requests, 12 of those requests have been sent and will execute in parallel. And we have two requests that are waiting in queue. So by enabling concurrent model execution, we can achieve a 4 times better performance and improve our GPU utilization with this particular scenario configuration. And so in this slide here, it's just showing the latency breakdown. So if you look here, with the red is the network and server. That's actually sending and receiving those requests. The orange shows us the time spent after the client has received that request. And the blue at the bottom of this chart shows us the actual client sending those requests. So, we will see a 4 times better performance with this latency breakdown. And this is the same scenario here with the 12 instances of the ResNet 50 model. Okay, and more charts here. The latency versus throughput. And we're using various batch sizes. So by enabling dynamic batching, we can almost get to nearly 2 million inference throughput for this particular scenario here. And so I think the last slide, I'm actually gonna skip. And I want to make sure that I touch on how you can use Triton Inference Server. So it's all open source, and we have a ton of examples in various applications, whether it's computer vision, NLP, text-speech, or ASR, automatic speech recognition. All of these examples are available on GitHub, and it's very easy, to get started. You can start, as I mentioned, on CPU. It does not require GPU. You will see benefits by using GPUs, though. And I think so the links are here. Can be found at NVIDIA Deep Learning Examples GitHub repo. And I think that's all we have, yeah. Thank you.
Excellent. Do we have time for questions? No, we do? Okay. We have just can y'all turn me on? Louis, please. Thank you. We have just a minute for 2 questions. So anybody want to ask one question? It was explained so crystal clear. Okay, all right. Oh, one question. Yes, Ruben.
Hi there. Just a question.
Here we go.
Hey, just a question. Just wondering, who are your competitors? Are you competing against the cloud platforms like AWS SageMaker? Do you have a hosted version? Because you mentioned it's open source. So how does your business function?
Yeah. Well, the business or Triton?
Yeah, so Triton specifically,
Yeah.
inference server.
So I wouldn't really say competitor in terms of AWS, but we have released a new version of Triton, NVIDIA Triton Inference Server that works with AWS SageMaker. So you don't have to really, decide which one per se. But within SageMaker, you're able to download the NVIDIA Triton Inference Server container from the marketplace, add it to your ECR, and then you can kick off your notebook session there.
Okay.
So yeah, so it works on
Thanks.
AWS as well.
Very cool. Excellent. Do we have one more? Any more? Okay. All right. Well, don't disappear if they have more questions. Thank you so much.
No problem. No sports questions?
I know,
Anything?
right? Thank you,
We're
Benika.
Cowboys fans, by the way.
Any others? Thank you.